Okay, hello everybody. It is April 6th, 2020. And today we're going to be talking about section 2.6. Okay, so this one's called a library of functions. Okay. All right. We've already talked about the first one. I guess I should say, I don't know. First entry in their library of functions are linear functions, which we spent a whole section talking about, but that's all right. Okay. So remember, these are functions that look like this, or that, we learned a couple different ways to write them. F of x equals mx plus b. That's linear. So there's some special cases, right? If m equals 0, it's a constant function, right? It's just f of x equals b, constant. Okay? And so you can't have, remember, x equal to a number. For example, let's say x equal to 3 is not a function. Because it fails the horizontal line test. I'm sorry, the vertical line test. Right? So if you wanted to draw that graph of x equals 3, it'd be this one right here. Right? This line right here is x equals 3. But if you had f of x equals b, like let's say for example b was 2, then this one is f of x. This one is definitely a function. It just has a very small range. Its range is 2. It mapped the whole x line, just the y value 2. Okay? Okay, and finally the last special case of a linear function is the identity function. So if m equals 1 and b equals 0, we have f of x equals x. So it's the identity function. Because it gives you back whatever you put in. So if I put in 1 for x, I get 1 back. If I put in 2 for x, I get 2 back. And so on and so forth. Okay, so the domain of a linear function is negative infinity to infinity. Because if you look at just look at this general form here, f of x equals mx plus b. There's no square roots and there's no division, so there's going to be no problems entering in any number in between negative infinity and infinity. Okay. Now, the range depends on if your linear function is a constant or not. So if m is equal to 0, the range is b, right? So that's like with this example. If f of x equals 2, in this case m is equal to 0, the range is b, which is just 2. But if m is not equal to 0, then the range is also negative infinity to infinity. Right? Because if I have some line here this is just some random y equals mx plus b line. No matter what x I put in here, there's always going to be some sort of x that gives me whatever y number I want. Okay, so that's why the range is also negative infinity to infinity if your m is not equal to 0. Okay. All right, so that's a little bit more about a linear function. So this is something we've already kind of done, but their first example is to write a linear function for which g of 1 equals 4 and g of negative 1 equals, I'm sorry, g of 3, negative 3, not negative 1, negative 3 is equal to negative 2. So it's kind of like, this is an ugly 4 here. So we talked about if you have 2 points, then you can find the slope that connects those 2 points. But they kind of gave us ordered pairs in function notation. So if you want to, the first thing you can do is figure out what these points actually are. So it would be, the x, you're plugging in 1, you're getting back 4. So it's 1 comma 4 is your first ordered pair. And the second one is negative 3 comma 2. Okay? So now it's just like all the examples we've done where you have to find the slope and then express it as a line. I guess we've just found the slope, but anyway. So let's start by doing that. So we use the slope formula. So m is equal to y2, so 2 minus y1, 2 minus 4 over x2 minus x1. So this is negative 2 over negative 4, which is positive 1/2. Oh, I'm sorry. What did I mess up here? Oh, yeah, I made a mistake. So here I wrote negative 2. This is the right example here. But I should have had a negative 2 here. So that changes this to a negative 2. But negative 2 minus 4 is negative 6, which is so this changes to a 3 over 2. Okay, so we found the slope. So to express it as an equation, right, or f of x is equal to mx, we found the m. So the only thing we need to do now is figure out what b is. So we're going to take our slope here, and we have f of x equals 3 halves x plus b. So you can take either one of these points because they do have to lie on the line. So let's just take the point 1 comma 4, and you plug it in for f of x and x. Okay, so you take 4. It's 4 is equal to 3 halves times 1 plus b, and now we can solve for b. So this is 4 equals 3 halves plus b. So then if I subtract 3 halves from both sides, you get 8 halves minus 3 halves, right? 4 is 8 halves, plus equals b. Okay, so this is b equals 5 halves. Okay, so now finally we can just write, oh sorry, and they were calling this, remember they called it g, not f, so I should have written g here and here. Okay, so g of x then is equal to halves x plus 5 halves. Okay, and if you would have used the point, instead of using the point 1, 4, if you would have used negative 3, -2, you would have gotten the same answer. Right, and we can check that. So if you do g of x equals 3 halves times our x value -3, oh sorry, so I need y value over here, plus b, then we have -2 is equal to -9 halves plus b, so this is, so, oh, I'm writing off the page here, right, so -2 equals 3 halves times -3 plus b, that was our other point, see, g of -3 equals 2, so this is -4 halves plus 9 halves equals b, which says that b is equal to 5 halves. So they work out. Okay. So that's how, if someone gives you 2 points, you can write an equation of the line that connects the 2 points. Okay. All right. So the next example is a word problem. So let me show you that word problem. Okay, so we have the largest known megatooth specimen is a tooth that has a total height, sorry, this is kind of getting, total height of 15.6 centimeters. Calculate the length of the megatooth shark from which it came by using the formula. Shark length equals 0.96 times the height of the tooth minus 0.22. Okay, so this is actually, this problem, we just have to use, so they give us an equation, right? The shark length, which is what we're looking for, but it depends on the length of the tooth, so shark length equals 0.96 times 15.6. Whoops, so here, let me write this actually. Height of tooth minus 0.22. Okay. Okay, so then, so this is shark length, what we're looking for. Equals 0.96, and now we can plug in our tooth height, so 15.6 minus 0.22. Okay, and so now if we do this calculation, if you put this into your calculator, you should get that the shark length is equal to 14.756, and that's in meters. Even they say that the equation works out so that if you input centimeters, you get meters back. So this is about roughly 48.6 feet. It's a pretty large shark. Okay. All right. So that's an application of a linear equation. So now let's move on to the next element of our library of functions that they want to talk about. So we're going to talk about we're going to talk about square root and cube root functions. Okay. So we already know we've already graphed in the last sections. We've already graphed y equals x squared, and the function y equals x cubed. Okay, but now we want to talk about y equals the square root of x and y equals the cube root of x. So the key difference here is when you have an even root and an odd root. So that's why we're talking about the 2 and 3. The 4, 5, 6, all these kind of follow the same pattern depending on whether the power is even or odd. Okay, so for example, if you have an even power, we know that if you take a look at the y equals x squared, if I put in 2 here, 2 squared is 4. And if I put in negative 2 here, we have negative 2 squared is 4. So remember, for functions, it's okay to have two separate x values go to one y value, right? That picture, so this is okay. 2, negative 2, mapping to 4. That is okay. But if you look at its inverse, the y equals the square root function, I'm calling it the inverse because if you have something squared and you want to get it, cancel out the square, you square root it. Okay, so sorry for just pulling that out of nowhere, but here, so if we want to do the same thing, if I plug in so this is called you want to take the principal root, right? So remember, whenever we take the square root of something, we always write plus or minus. So this function here actually specifies that you're using the positive square root, okay? Right, because the square root of 4 could be negative 2 or positive 2. But remember, you cannot have 4 as an x value mapping to negative 2 and 2. You can't, that's failing the vertical line test. So instead what they do when they have an even power here is they call the positive one the principal. Square root function. Okay, so essentially they're just picking one, right? And then if you had the fourth root, there would be 4 different things you'd have to pick from, okay, and so on and so forth. So if we wanted to graph this, we're going to graph the right, and that's why we actually say that taking the square root of a it's not so much the fact that we're taking the square root of a negative number here. It's the fact that if I put in 4 to this function, I have to decide which root I'm getting back. I'm not putting in a negative number here. We know that that's against the rules. Okay, so for graphing y equals square root of x, if you draw your graph here, you only need to worry about the positive numbers because remember the domain of a square root function has to be positive. It's 0 to infinity. Okay, so we might as well map 0 first. That goes, the square root of 0 is 0. So 0, comma 0. Let's go ahead and do, we have, here, we'll do that here. 0, 1. The square root of 1 is just 1. So that goes right there. So now if I go, make this a lot longer here. 2, 3, 4. So the square root of 4, right, and we're choosing the positive. And if I go out to 5, 6, 7, 9, you get up to 3. So it's kind of this, it's not linear, but it's like a curve. It's concave, which means it has like a concave down shape. So it's not a line, that's just my poor drawing. Okay, so that's how you would draw the square root function. So the cube root function is different because you can take the cubed root of a negative number. Okay, so the cubed root of a negative number it's just defined, right? So if I put the cubed root of -8, I know that -2 times -2 times -2 is -8, and there's no other three numbers that are the same number. Like you could have -2, 2, and 2, but that's not the definition of cube root because all three of the factors have to be the same number, right? So -2 and 2 are not the same number. But the cube root function has a domain of infinity to -infinity to infinity. So let's go ahead and draw our graph here. So instead of going up by 1s on the x, I'm going to go up by 2. So I got 2, 4, 6, 8, 10, and -2, -4, -6, -8, and 10 over here. And we'll go 2, 4, 6, -2, -4, -6. So that's the y. Okay, so again, we're just going to take, 0, the cube root of 0 is 0. The cube root of -1, so if I'm here, is -1. So it's right there. And then if we go out to 8, the cube root of -8 is a -2, so it's right there. So now, if I take the cube root of 1, we get a 1. And if I take the cube root of 8, we get a 2. So we got the cube root function kind of looks like that. Okay, so that's how you would graph those two. So that's all we're going to talk about today with those. But it's just make that key difference that if you have to really look at the power of your root to determine what the domain is, right? And then if you have an even power, we usually graph the principal or the positive roots. Okay. And yeah, I'm sorry, I should have said. So actually, right. Okay, so now we're going to talk about piecewise functions. And actually, before we do that, I'd like to do one more example. So this one is graph relating to the two we just did. Graph the square root of -x. Okay, so some of you might be saying, well, you just said that we can't take the square root of negative numbers. Okay, but what if I put in negative numbers for x, then a negative times a negative is positive. So this one's domain is actually -infinity to 0 included, right? Where the domain of x of root x, y equals root x, was all the positive. It was 0 to positive infinity. The domain of this example is actually going to be 0 to negative infinity, or negative infinity to 0. Sorry, I said that backwards. So it's going to look just like the square root function here. So if I go 2, -2, -4, -6, -8, -10, -12, -14, and -16. So you got 2, 4, and 6. Alright. So if I put 0 in here, you get a 0 back. If I put in negative 4, it's negative negative 4, so it's the square root of 4, which is 2. And then if I put in 9, you're going to go up to 3. 1 would be 1. And 16, you'd get up to 4. So, right. That's the graph of negative y equals square root of negative x, right? Because if I put in a positive number, you're taking the square root of a negative number in this function. Okay. All right. So let's move on. Now we will start talking about piecewise function. Okay. So a piecewise function is it's where you can, like the graph of a piecewise function might look like this. So for some, let's say for 0 to 2, you have a function that looks like the square root of x. So it goes like that. But then from 2 to 5, you've got one that's just a steep line like this. So a piecewise function is where you have kind of the combination of two different functions depending on what interval you're on. Okay, so for example, the first example is let f of x equal, so the way they write this is they do this like curly bracket, and you can have as many of these here as you want. You can have like, when I say these, I mean like as many functions and intervals as you want. So with every piecewise function, you need an interval here. So it's x squared if x is less than 1, and 2x plus 1 if x is greater than or equal to 1. Okay, so it says find f of 0 and f of 2. Okay, so think about this here. So if I wanted to find f of 0, usually we would just plug in 0 here. But which one do I plug it into? Well, the definition of this capital F depends on what value I put in for x, right? It's either going to be x squared or 2x plus 1. Wait a second here. Right, so I have to look, is 0 less than 1 or is 0 greater than or equal to 1? Well, 0 is less than 1, so I should use this definition here. So f of 0 is equal to 0 squared, since 0 is less than 1. So equal to 0. Right, so now what about f of 2? So 2 is not less than 1, but 2 is greater than or equal to 1, so f of 2 equals 2 times 2 plus 1, which is 5. Okay, so it all depends on what interval you fall in here. Okay, and we call these points, so this point x equals 1, right? If it's less than 1, we have this x squared definition, and if it's greater than or equal to 1, it's this definition. So we call this point x equals 1 is called in the book it's called a turning point. Okay, so you can have as many of these as you want, turning points. The bracket gets longer and you have more functions. Okay. All right. So another word problem that we can discuss. Okay. So, oh yeah, I'll show you guys the problem that we're talking about. So, okay. So in Peach County, Georgia, a section of interstate highway has a speed limit of 55 miles per hour. If you are caught speeding between 56 and 74, your fine is $50 plus $3 for every mile per hour over 55. For 75 and higher, your fine is $150 plus 5 miles an hour for every mile over 75. So they want you to find the piecewise function that gives your fine, what is the fine for driving 60 miles per hour and what is the fine for driving 90 miles per hour. Okay, so the first thing we need to do is find the piecewise function. Okay, so you can go 55 miles an hour, and that's legal, but if you are in between 56, so we're going to say x is the speed, right? And we'll call this f of x is the fine. Okay, so there's two different intervals here, right? It's 56 to 74 miles an hour. Your fine is $50 plus $3 for every mile per hour over 55. But once you move into the 75 miles per hour and over range, your fine is defined differently. It's $150 plus $5 an hour, or $5 for every mile an hour over 75. Okay, so if I'm in that first interval, if x is less than or equal to so you could do x is less than or equal to 74, but greater than or equal to 56, or you could do if you wanted to make this the best way to define it is actually you want it to go up to 75. So everything up to 75, that's why we use a strictly less than here at 75. So if you're going like 74.5, you can include that in this one. So 75 would be a turning point, right? So now the other definition comes that if x is greater than or equal to Okay, so this one says that it's $50, so automatic fine of $50, so plus 50, and $3 for every mile over 55. So we have to change this a little bit. So it's like 3 times x minus 55, right? Because we need every mile an hour over 55. So if I just put x here, and I was going $58, I would get charged 3 times 58 rather than 3 times 3. Okay, so the same thing here. So this one says it's 150 plus now 5 times every mile and over 75. Okay, so that's the definition of our piecewise function there. Okay, and we can tell that it's just two linear functions, right? I could distribute this 3 out, and then I'd have 3x minus, let's see, it'd be 165 plus 50, so it'd be 3x minus 115, right, if you want to write it in slope-intercept form. And you could do that same for this second piecewise part. Okay, so that's part A. Part B was find f of 60. So, is 60 in this interval and this interval? Well, 60 is in between 56 and 75, so we're going to use this definition here. So it's 3 times 60 minus 55 plus 50. Right, and you probably could have answered part B and C with just by, okay, well, part B is I'm going 5 miles per hour over 55. So that's 3 times 5, that's $15 plus 50 is 65. But let's see if we get 65 back in our definition here. So it's 3 times 5 plus 50, which is 65. Okay, that's good. So that would be your ticket. You'd have a $65 ticket in Peach County, Georgia. Okay, so what about C? Find f of 90. Okay, so f of 90 is definitely bigger than or equal to 75, so we have to use this definition. So it's 5 times 90 minus 75 plus 150. Okay, so this is 5 times 15 plus 150, which is 45 plus 150 which is a $195 ticket. Which is, I mean, relatively, like if you're going 90 miles an hour in a 75, that's pretty cheap. Okay. Alright, so that's how you would do that problem. Okay. Okay, so the next example for piecewise functions is construct the line graph from the data Okay, and the data is time versus value. So we have 1, 1, 3, 5, and 5, 2. Okay, so the line graph means you just take these points. I'm drawing this graph here. We got 1, 2, 3, 4, 5. So the point 1, 1, 3, 5, and 5, 2. The line graph just means the graph that connects those lines. So this is a function. It passes the horizontal line test. Or, sorry, not horizontal, vertical line test, right? Doesn't pass through 2 points. So we want to write this as a piecewise function. So one of our intervals is going to be, if we're in between 1 and 3, we need to figure out what this line is. And if we're in between 3 and 5, we need to figure out what this line is. Okay, so for example, if we've already done, if I give you these 2 points, you should be able to tell me what the equation of that line is that connects those 2 points, and vice versa. If I give you these 2 points, you should be able to tell me what the equation of this line is. Okay? So we're going to do that. So you just have to do, it's like two example ones in this problem, right? So I need to find, you first find those intervals. So the intervals are 1 to 3 and 3 to 5. So for 1, 2, so for x less than or equal to 1, less than or equal to 3, right? And these are colored in dots, so we need to include, that's why it's a less than or equal and not just a less than in here. Okay, so for x, we need to connect the point 1, 1 and 3, 5. So first we can figure out what the slope is, right? That's our slope formula. So it's 5 minus 1 divided by 3 minus 1. Okay, so that's equal to 4 over 2, right? So that's equal to 2. You could have also just seen that from the graph, right? If I'm going up 2 over 1, or I go up 4 here and over 2, that tells me that the slope here is up 4 over 2, which is 2. Right, and I could do the same thing here. I go, let's see, it goes down 1, 2, 3 and over 2. So the slope here should be 3 over 2. But negative, right? Because we're going down from left to right. And this one's positive because we're going up. Okay. All right. So now we have y equals 2x plus b, and we still need to figure out what the b is. So we pick either 1 comma 1 or 3 comma 5 and plug it in here. I'm going to do 1 comma 1 because 1 are easy numbers to work with. So we get 1 equals 2 times 1 plus b. Okay, so if I solve for this, it's 1 minus 2 equals b. So b equals negative 1. And right, remember that's the y-intercept. So if this function were defined when x equals 0, if I go in right, I'm going up 2 over 1. So up 1, 2 over 1, the y-intercept should kind of be at negative 1. Does that make sense? That's good. Alright, so that's our line for this interval. It's y equals 2x minus 1. Okay, what about the other interval? So what if we're going from 3 less than or equal to x less than or equal to 5? Well, then I have to connect 3 comma 5 and 5 comma 2. Okay, so m, we've already seen this on the graph, but m is going to be 2 minus 5 divided by 5 minus 3. So that's negative 3 over 2. Okay? So now here we have y equals negative 3 over 2x plus b. Okay, and it's not the same b, right? Like, this is going to be different. So now I can pick either of these points and plug it in here. So let's do the first one. So 5 has to be equal to negative 3 halves times 3 plus b. So this is 5 is equal to negative 9 halves plus b. Excuse me. So 10 halves, right, that's 5, plus 9 halves is equal to b. That's after I add the b to both sides and write 5 as 10 halves rather than 5. So this is 19 halves equals b. So our line for this interval is y equals negative 3 halves x plus 19 halves. So the way you would write this piecewise function that connects these dots, this one, is f of x equals curly bracket. So if we're in between 1 less than or equal to x less than or equal to 3, and this one is if we are 3 less than or equal to x less than or equal to 5. Negative 3 halves x here plus 19 halves. And this one is going to be 2x minus 1. Okay, so that's that example. So the last one with the piecewise function is actually a function you've seen before, but you might not have thought it was a piecewise function. It's they want you to graph y equals the absolute value of x. So another way to write the absolute value of x is as a piecewise function. So it's x if x is positive or 0, and negative x if x is negative. Right? Because if I plug in 0, right, you could have made this one greater than or equal to, or just greater than, or less than or equal. Like, if you make this a strict inequality, then this one has to be a non-strict inequality. But you have to include a 0 in one of these definitions. But 0 and negative 0 are both just 0, right? There is no such thing as negative 0. Okay, either way. So now if I plug in 1, if I put 1 in for x, then if I look at this, it's, well, 1 is greater than or equal to 0, so I spit back out positive 1. Now if I put a negative 1 in here, well, negative 1 is less than 0, so I need to take negative 1, which gives me positive 1, or the absolute value of negative 1. So this is the way you piecewise define an absolute value. Okay, so if we're going to graph this function, then we need to draw our graph. And let's say, so we already figured out that 0 is 0, and we figured out that the absolute value of 1 is 1, right? And you can just keep filling these in. So it's actually, think about graphing x, y equals x on the positive end. That's a slope of 1 with a y-intercept of 0. So 1, 2, 3. So right, it's just up 1 over 1, up 1 over 1, up 1 over 1, and y-intercept of 0. So on the other side, though, it's a slope of negative 1, so we go up 1 to the left 1, up 1 to the left 1. With a y-intercept of 0. So that's how you graph y equals the absolute of x. Okay. All right. How about another graphing problem? Graph f of x equals piecewise definition negative 2x plus 1 and 3x plus 1. So this one's if x is less than 1, if x is greater than or equal to 1. Okay, so we're calling, remember, this 1 is our turning point. In the absolute value function, 0 is the turning point. So here we go. Let's get both of those in there. So I need 1, 2, 3, 4. Okay, almost done here. Okay. So there's my graph, my axis. So now let's look at the first. So if we're less than 1, so if we're here and over, then we need to graph negative 2x plus 1. So, okay, so I know that the y-intercept has got to be, the y-intercept was when x equals 0. That's in this one. So I know that the point 0, 1 is on that graph. So then I need to go, since it's negative, you go, it's up 2, but then over to the left, negative 1. Up 2, over to the left, negative 1. So it'd be this line right here. Oopsies. Okay, but we need to go all the way to positive 1, and then when we get to positive 1, this positive 1 should go down to, right, if I plug in, if I had negative, if I were able to plug negative 1 into this definition, it would be negative 2 times negative 1, I'm sorry, positive, negative 2 times 1, which is negative 2 plus 1, so we go down to negative 1, right? And that's the same, it's like down, you're going down 2 over 1, because it's a negative 2 slope. So, but the problem is here is we don't want to include 1 in this function, so we need to put a circle here. That means we don't include it. If I wanted to evaluate f of positive 1, I would use this definition. not this one. Okay, so now if we graph this side, so if we're greater than 1, we still have a y-intercept of 1. So if we're here, the slope is 3. So here we can just start graphing. So if we pick 0, 1, so we know the y-intercept here is 1. So, but that's not in our graph. So if we started here and we go up 3 over 1, this point is going to be on our graph, right? Because that's when x is equal to 1. If I plug in 1 here, it's 3 times 1 plus 1 is 4, so 1 times 4. Then you go up 3 over 1. Oh, this is tough. Okay, so this one would be, kind of draw that. So that would be your piecewise graph, even though it's a bad picture. Okay? Alright. Okay, so the last one that they want to talk about in this section here is the step function. Okay. So it's a special kind of piecewise function. Step function. Okay, so this one says graph the greatest integer function f of x equals, so they have these weird curly brackets, or like these weird brackets here. That means greatest integer. So for example, if you said, if I put in right, if I put in, for example, f of 2.5, that's going to go to 2. It's basically just rounding down, no matter what. So if I put in 3.9, this is equal to 3. And so on and so forth. So we need to figure out a way to define this piecewise. So if I wanted to find this piecewise, so also we have to think about, what does it mean if I did f of negative 2.1? Well, that's going to be actually negative 3, because we actually round down, right? And think about it. If you were to call this negative 2, you'd be rounding up, right? Because the negatives go from left to right, right? So like negative 3 is smaller than negative 2 is what I'm trying to say. Okay, so right, so we need to figure out how to define this piecewise. So it's actually going to be, there's infinitely many turning points. So f of x, so I'm just going to draw this curly bracket. So we're going to use dot 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 notation to mean infinitely many. But if I'm in between x is less than, oh, and also if we have f of 2, for example, that's just going to be equal to 2, right? So you're still rounding down. So if I'm in between 0 and 1, right? If I have like 0, 1.2, or I'm sorry, 0, 0.2, 0.7, you always round down to 0. Okay, so 1 here if I'm in between 1 but less than 2. So that goes on forever. And then if we get negative 1 if negative 1 is less than or equal to x, which is less than 0. And that goes on forever Okay, so great. We've got the definition figured out, but how do we graph it? So the way you graph it is we'll just do a couple of them. We don't have to draw infinitely many of them. So 0, 1, 2, 3, 3, negative 1, negative 2, and negative 3, 1, 2, 3. Okay, so if I'm in between 0 and 1, I need to have 0. So it's just this constant function, but I include 0 and don't include 1 because that's my interval here. So now if I'm in between 1 and 2, I need to graph it at 1. So it's like that. And then again. So this is why they call it the step function. Because it looks like a step. It looks like steps. Okay. So they often remember. So in the last section, in the last couple of sections, we've talked about graphing functions, and then last time in 2.5 we talked about or in 2.4 we also talked about the domain and range, and how to find those from the function itself by looking at a graph. And in this one we just talked about some functions that people kind of often use in the graph. So remember, we need to keep in mind finding the domain, and range of functions. Whether it's increasing, decreasing, or constant on given intervals, right? It doesn't have to be always doing that. Or sometimes it's even or odd. Okay. So for example, if we looked at back at some of our examples here, right. So if I looked at the simple identity function, or not identity, a constant function, f of c equals c, f of x equals c. So that's like this one right here. So if I go up to, let's say this is the y value c. So this is my function. Then the domain of that, again, is negative infinity to infinity. It's constant from negative infinity to infinity, and it's also it's even, because if I plug in positive x, it's the same thing as if I were to plug in negative x. Its domain is negative infinity to infinity, and its range is actually just this one value c, because it's the only thing that gets mapped to. Okay, but if I were to talk about another one that we've talked about, this identity function, right, f of x equals x, then it's looking like this. It's a linear, right? M is 1 and b is 0. So the domain is negative infinity to infinity, and the range is negative infinity to infinity because it's a linear function. There's no square roots. There's no dividing by 0. There's no piecewise definition. So its domain and range are negative infinity to infinity both. Now this one is an increasing function, right? Because it's on negative infinity to infinity. It's because remember, the definition of increasing is if I have one x value that's smaller than another x value anywhere in this interval, then an increasing function will be f of that smaller x value is going to be smaller than f of that bigger x value. Okay. All right. So what about the absolute value? So what if I did f of x equals absolute value of x. So, oh, and this one's also odd, right? Because if I plug in, for example, 2, like f of negative x is equal to negative x. So it's, which is equal to negative f of x. So that's why it's odd. So in this case, if I do the absolute value, right? We graph that as an example. The domain is negative infinity to infinity. You can take the absolute value of negative number, but the range is only 0 to infinity. Because if you take the absolute value of a number, you're only going to get back a positive number. Okay. And it's decreasing, right? It's got a negative slope from negative infinity to 0, and it's increasing from 0 to infinity. And it's also an even function, because if I plug in negative x, it's still going to be absolute value of x. Okay, so we can do this with all these functions that we've graphed, finding these properties about these functions. Okay, so just keep that in mind when we're doing our homework, and that's all I have for the lesson today.